while I'm waiting for everybody else to log in, Jeff, I sent you a reply to your question about lab for next week. So you should have a look at that. I think I've got 2 more people that I need hopefully to show up. Just because this is probably of interest if you are not graduating this semester. There was a meeting held today by some of the High Muck Muck faculty admin people about the way the fall semester is possibly going to work. Obviously, they haven't resolved all the details yet, but they are looking into expanding to more face-to-face classes. I haven't been told exactly how that affects my classes, and this is for fall of this year. I think the summer is going to be largely the same way that it is currently, where at least people are taking chemistry. We're still sticking with the half and half version. But pretty much all of the lectures are tending to stay with the Zoom mode. But the idea, I think, is that at least some lectures would be held face-to-face. I don't know if that's like a once a week thing. There's also a discussion, just so you guys know, that some of the daytime classes, I'm not sure if this actually applies to night classes or not, that they are looking into the possibility of Monday, Wednesday, Friday, which is a really traditional 4-year university way of offering classes. I know that on a TCC mode, because we assume that a large percentage of our students are working, classes tend to be offered Monday, Wednesday, or Tuesday to Thursday as far as lectures go, with lab often being on a different day currently. But there is some discussion going on that there may be some Monday, Wednesday, Friday classes being offered for the fall. Like I said, I'm not sure that would be night oriented, just because classes on Friday evenings, I don't know whether that's problematic or not. I know that there's Saturday classes. My daughter's enrolled in a Saturday class. She takes a particular art class from 10 to 12 on Saturday mornings. So, and I know that there is often a Saturday section of Chem 111, if you have friends who have yet to take that, that is also sometimes offered on Saturdays. So things are changing somewhat, but actual details are kind of iffy at the moment. So file that as potentially useful information if you have classes yet to go for other subjects. So hopefully that's at least sort of useful information. I don't see my other 2 people in the waiting room yet. All right, before we dig back into equilibrium, since homework for kinetics is due tonight at midnight, are there any remaining questions about the kinetics chapter? It is going to be half of the next test, which as current mode is probably going to be like right after spring break, because I don't know. I don't think we're going to finish equilibrium tonight. We might finish equilibrium on Tuesday, but then I need to give you a chance to turn in homework so that we can then go over it prior to a test. So the weekend directly after spring break is a highly likely time for test number 2, which covers kinetics and equilibrium. So questions about kinetics. All right, we are going to dig back into equilibrium then. All right, on Tuesday, we kind of ended with looking at a couple of different equilibrium scenarios, talking about the Kc and the Kp, which sometimes match, but sometimes do not. And I gave you a first example there that had 2 molecules on the left and 2 molecules on the right. So the delta N value of that particular equation would be 0, which would give you an equivalent Kp and Kc. And then we looked at the other equation, which was a decomposition one, for CoCl2 falling apart into CO and Cl2, because there's 1 molecule on the left and 2 on the right. That means your delta N is not 0, your delta N is 1. And this will give you a different value for your Kp than your Kc. So keep in mind that your temperatures, when you are using this formula, must be done in Kelvin in order to make it match the 0.0821, which is the same conversion constant that we use when we are doing ideal gas law of liters atmospheres per moles Kelvin, as opposed to the one that we're using for the enthalpy lab, which is indirectly based on 62.37, because that's in millimeters mercury. All right. Here is a reaction you will probably see a lot of. It is both in your textbook and possibly in your lab book, and if you go scrounging around for other examples, lots of textbooks pick on this one. PCl5, which is a gas, falling apart into PCl3 and Cl2. All of these are in the gaseous phase, which means I can either deal with them in terms of pressures, or I can deal with them in terms of molarity. So I picked on pressures to do this example. I have a Kp value of 1.6 times 10 to the negative third. It's at 80 Celsius, although that's not of great importance for this particular version of the problem. I know that my PCl3, and I realized I forgot to put my unit there, so ATM, just so that it matches the ATM for the Cl2. So 0.75 atmospheres for my PCl3 molecule, 0.31 atmospheres for my chlorine molecule. I want to find out what my original reactance pressure is. Rule of algebra says if I only have one reaction or one equation, I only get to solve for one unknown, which is fine. That works for this. We have a situation where put in your values, put in your Kp of 1.6 times 10 to the negative third, put in your 2 top values there of 0.75 and 0.31. The bottom pressure is your only unknown. Finish your number crunching, and you end up with 145.3 atmospheres. Now go back and look at your Kp. Remember, we made some generalizations about K values at the beginning of the chapter here. One of the things we said was that Ks that have values 10 or bigger tend to have heavy favoritism toward the products, meaning you're not going to have a whole lot of reactants left. It's all pretty much going to go forward in your reaction. In this case, we have a pretty tiny K value, definitely less than 0.1, which was the other benchmark we were looking at. And so it makes good sense then to end up with a pressure that is much larger for the reactant than for the pressures of the products. We've got 145.3 versus 0.75 and 0.31. One of the things that you see a little of, but not a lot, is some discussions of heterogeneous equilibria. Now, we've dealt with the heterogeneous stuff in a couple of different versions. We even kind of mentioned it in terms of catalysts and some other things like that. What we're dealing with here is a situation where you may have solids as part of your reaction. Now, because a solid is not dissolved in anything, it neither has a molarity nor a pressure. Therefore, we're going to kind of do an approximation, and then we're going to kind of resolve that. So our version here of a reaction that has a solid in it is ammonium selenide, which is a solid at room temperature. However, if you let it sit there for a while, especially if there's a little warmth to the place where it is, you will begin to get some NH3 and some H2SE. So ammonia gas and hydrogen selenide gas. Now, look at my equilibrium expression and note it has a prime in it. Kind of that's not, I did not mean to highlight all of that. Give me a moment. And I squished everything upward. All right, so that bit. No, now it's not being cooperative. All right. There. Okay. So the little part I highlighted there, we have a prime or an apostrophe, also known as a prime in most math classes, which means it's kind of an in progress and not yet finished version of the reaction. So I'm going to go ahead and write everything into it, but it's not really truthful because it does include the solid part. I'm still following the profile of products over reactants. I've got 2 ammonias, so NH3 squared. I've got 1 hydrogen selenide. I've got the ammonium selenide on the bottom there. But I know that it's a solid. So in order to make this more correct, I would want to then delete my, oops, I'm hopping lines again here. I would want to delete my solid. This basically eliminates the bottom half of your equilibrium expression. It does sometimes happen. You won't see a lot of it, but there is a possibility when you have solids present that you may have no lower portion to your equilibrium expression. Note that if I write my Kc this way, I've got the ammonia squared and the hydrogen selenide. If I write it in the Kp version, I've got P squared of ammonia and then P of H2SE. A little bit about the theory that goes behind this. Anytime you have reactants that are turning into products, and the fact that we are dealing with a reaction which is capable of going both forward and backward, in fact, at the same time. Remember when I was talking on Tuesday, if I weren't typing this in Microsoft Word, I could make it appear to have an arrow on the top of that long looking equals symbol that looks like an arrow missing a half of its tip. On the bottom, it would be going back in the opposite direction. Let's revisit that idea here for a moment. So this is kind of the stereotypical way that it is written when we're talking about reactants versus products. And let me move my edge here so this actually looks more normal here. So reactants, okay, and then this side would have products. Oops, I don't know if I spelled it correctly. I'm hitting the wrong buttons. Products. All right, so reactants, products, and you have that weird kind of double-headed mutant-looking arrow set that's in the middle there. Like I said, I can't make Microsoft. I have never figured out how to make Microsoft do that. So we're kind of stuck with what looks like a giant equals sign in my notes. So because your Ks for the forward and the backward, R for reverse, are happening at the same time, we can kind of look at this from a theoretically, how does the math work point of view. The forward rate is based upon Kf and the A and the two B's, so it becomes B squared. The reverse is based upon the K for the reverse direction and what we view as the product, AB squared, or AB2 rather. And if you're at equilibrium, if you're already at equilibrium, we can therefore assume the rate forward equals the rate back, which allows us to then make the further assumption of Kf AB squared equals Kr AB2. If you set it so that it looks more like a typical equilibrium expression, you get Kf over Kr, you get products over reactants. And since we're dealing with square brackets, we are going to call this a Kc as opposed to a Kp. As long as you are not changing your temperatures, we assume that the forward and reverse rates are equivalent to each other. So we looked at magnitude. Is it less than 0.1? Is it bigger than 10? Or is it somewhere in the middle? One of the things we need to kind of roll back to for a moment is the K value and the time to get to equilibrium are actually not directly related. And I know that sounds weirdly backwards, because if you have a K of like 5,000, that would make you think that, oh, it's one of those zippy reactions that takes half a second to happen. No, the K only tells you I get lots of reactants if it's equal to 5,000. It could take hours or days for it to reach the equilibrium. The way you determine How fast you reach equilibrium has a lot more to do with activation energy. Activation energy being part of the previous chapter. So that if you have kind of average, often sometimes they will tell you 50 to 100 kilojoules per mole is kind of an average activation energy. That will give you a moderately fast reaction. If you have a much lower activation energy, chances are it will give you more time, or it will take more time for you to get all the way over to equilibrium. And if you have a huge activation energy, yeah, then it could take like years maybe, because it has to push over the hump to get over to the product side. We will come back to equilibrium, or to activation energy again later, because it was a chunk at the end of the kinetics chapter, and it does appear a couple more times in the later chapters. All right. What if you're not at equilibrium? What if I dump two things together in a beaker and it hasn't gotten to the equilibrium point yet? Is it going to backpedal, shift left, because it thinks there ought to be more reactants? Is it going to lunge forward, shift right? Or did you happen to already actually be at equilibrium, which is a possibility? One of the things that happens here is that when you first dump things together, it is known as a Q value. And I like to maintain, and this doesn't entirely agree with your textbook, but it agrees with another textbook that I really like. I like to make it match. KC and QC go together, as well as QP and KP. That way you can kind of know what you're dealing with. Am I dealing with concentrations, or am I dealing with pressures? So what if I compare them? If I have initial values, and those, once I crunch them through the equation, give me a reaction quotient bigger than the K value, it means that it is going to backpedal to the left because it thinks there ought to be more reactants involved. If they equal each other, K equals Q, you actually happen to be at equilibrium then, which then gives us the last option of, well, what if Q is less than K? It thinks that you need to go forward to the right. It thinks that there ought to be a lot more products by the time you get to equilibrium. All right, let's look at one here that involves nitrogen reacting with 3 molecules of hydrogen, and it gives you 2 of ammonia. You're given information that says KP is 315. And you start with, okay, so that's your tip off. Start with means find the Q so that you can compare it to the K. My starting points are 0.15 molar for the nitrogen, 0.73 molar for the hydrogen, and 0.55 molar for the ammonia. Does my reaction proceed left? Does it proceed right? Or does it just sit there and spin? Which means that it's at equilibrium. All right. Write your equilibrium expression. Products over reactants with appropriate exponents. My NH3 is squared because there is a 2 as a coefficient for my ammonia. My H2 is cubed because I have a coefficient of 3 with my hydrogen gas. Put all your values in. I put them in parentheses to differentiate a little bit to indicate that I was in the process of doing the math here, as opposed to the square brackets. So 0.55 squared, 0.15, 0.73 cubed, crunch all your numbers, and you end up with a value of 5.2. So if I compare that to my KC, 5.2 is smaller than 315. So I am in the situation where it is going to shift right toward products. So toward products, if I add in this here, shift right. Okay. Now we get to the situation of, what if I know my K and I know some of my initial data, but not all of it? I'm going to assume that it's going to go toward equilibrium. Now we begin to embrace the ice method. Remember I said you're going to see a lot of this particular reaction here. It's the one that everybody likes to pick on. So PCl5 makes PCl3 and Cl2. I know that for whatever temperature I happen to be at, my Kc value is 0.0211. So little bit of a thought to start right there. I have a kind of small K value. So chances are once I hit equilibrium, I'm not going to have a whole lot of my products here. So I'm going to set it up assuming that my initial concentration is 1, assuming that I have 0 products. I want to find out what the equilibrium concentration is of everything. All right, start with your equilibrium expression, because that's kind of the basis for all of this. Do your products over reactants, put your 2 products on the top and your 1 reactant on the bottom. All right, and the reason it's called the ICE method is that's just sort of a acronym, shorthand. ICE, initial, change, and equilibrium. So you have to set up a little chart to help you keep track of your data. Having spent way too much time helping my big kid with his physics, this is kind of like drawing free body diagrams for physics. You have to like draw your stuff out so you know what you're doing with it. My PCl5 is 1 molar. I have no PCl3, and also I have no Cl2. So think about this in terms of the equilibrium. If I don't have anything at all on the right-hand side, once I achieve equilibrium, at least a little bit has to end up on the product side. Now, it might be a small amount, but it has to not be 0 when I'm done. Now look at your change line. In order to make it flow forward, I need to take away a little bit of my reactant, PCl5, so minus X, and make a little bit of PCl3 and PCl2. Why are they all ones? Okay, why is it minus 1x and plus 1x and plus 1x? Stoichiometry. Because my initial reaction, I'll scroll back up here for a second. My initial reaction had 1 and 1 and 1. 1 PlCl5 makes 1 PCl3 and 1 Cl2. This is why all your X's are 1 in this case. All right, continuing on down the ice chart. Well, in order to figure out what those values are at equilibrium, now we head toward the algebra. At equilibrium, your PCl5 is 1 minus X, and 0 plus X is just X for both PCl3 and Cl2. All right. Now put your algebra bits into your equation. X and X on the top, 1 minus X on the bottom. But I actually have a number value for my Kc. Back at the beginning of the problem, we said it was 0.0211. So we get to the point here where I'm actually kind of have everything that I know. So this part here in yellow is once I actually have all my pieces, I've got a value for K. I have both of my reactants dealt with on the top because it's X times X, so that's X squared. And I have 1 minus X on the bottom. Now we get to embrace the algebra. Quadratic equation stuff. Remember that in setting up a quadratic equation, you want to have 0 on one side. It actually doesn't matter whether you put it on the left or the right. And on the opposite side, you want to have it be in the format of ax squared plus bx plus c. So I rearranged this. I made sure I kept track of my signs. So I end up with x squared plus 0.0211x minus 0.0211. I pulled all of my values over to the right-hand side so that my 0 ends up on the left in this particular case. All right. Now we get my quadratic thing. And this is another one where I'm having this problem of I can't show you where the square root is because of the way Word works. But this little part here, I sort of vaguely highlighted in blue there. Remember that when you're doing algebra, all of that's under the square root sign. Okay. So minus b plus or minus under the square root b squared minus 4ac all over 2a. So let me go back over to my whiteboard to refresh your memory on how this looks. All right, so we're going to have minus b plus or minus, and all of this is under the square root here, b squared minus 4ac, and all of this is over 2a. Okay. Dredge quadratic formula out of your memory from previous math classes. All right. Now I'm going to put all my numbers in. And I didn't show you all the crunching. I showed you part of the crunching here. Remember that quadratic formula gives you two roots. You cannot have negative molarity. So you will basically always have one root that just gets tossed out because only one of them will end up giving you a valid answer. In this case, it was the left-hand one. I have negative 0.0211 plus 0.2913 over 2 because it's 2 times 1. And my x value ends up being 0.135. Not quite to the end. I have to go back and make sure I actually know what the values are for all three of my molecules. We had 1 minus x as part of our ice chart, so I have to do 1 minus 0.135. So my equilibrium expression of my reactant was 0.865. My other two molecules, which are both products, are identical to each other. They are both the x value. So they are both 0.135. Let me give you another variant on this. Here's a reaction that has hydrogen gas and iodine gas, and they will form hydrogen iodide as a gas. And there's two of them on the product side. I'm going to start with identical amounts, half a mole of hydrogen and half a mole of iodine. And note, they are put in a 1 liter flask. This is your tip that we are actually dealing with molarity at this point. So half a mole in a 1 liter, that's half liter, that's 0.5 molar. Calculate my Kc, or look at my Kc so that I can calculate my equilibrium concentrations. This time around, I have a big Kc value. So I will probably get much higher product values and much lower reactant values. Set up your ice chart. H2, I2, HI. It is to your benefit to put them in the order that they appear in the reaction when you construct the chart. We have 0.5 and 0.5 and 0. We had no products to start with. This time we are again flowing to the right, but I have a coefficient. When I look at my reaction, I have 2 molecules of HI. I can't just say plus X. I have to say plus 2X. For my equilibrium, then it's 0.5 minus X for both of my reactants, and 0 plus 2X is still just 2X for my product. Plug it all back into your equilibrium expression. Products over reactants. Make sure that your HI is squared. And yes, this does actually mean you use the number 2 twice here. My Kc value is 54.3. That 2 that was in your original reaction as a coefficient does get used inside and outside. I have 2x squared. And then on the bottom, I have 0.5 minus x twice because I have 2 reactants. So I should probably also have, well, I'll just sort of mention it. When you look here at the 2x squared, remember, if you actually multiply this out, you get 4x squared. 2 times 2 is 4. X times x is x squared. I'm going to take a square root of both sides. Okay, let me flip back over to my whiteboard. All right, so I had 54.3. That's on my left-hand side. And I've got 2x and in parentheses squared. And on the bottom, I've got 0.5 minus x and 0.5 minus x. Just to make sure that you understand what I'm doing here. I'm doing square root of this side, and I'm doing square root of this side, okay? That way I get a number value on the left, but I do actually still have some x's left on the right-hand side. So once I take the square root, now I've got square root of 54.3 is 7.37. I rounded it a little bit. Square root of the top is just 2x. Square root of the bottom, because they're both the same, is 0.5 minus x. Continue your rearrangement. Bring your 0.5 minus x up to the left-hand side. Multiply it together. I get 3.685 minus 7.37x. I've still got a 2x on the other side. Move my x, because I'm adding positive 7.37x to both sides. I end up with an x value of 0.393. So now we have to still kind of tinker with this just a little bit, because way back up here when I did my equilibrium ice chart thing here, none of those are just an x by themselves. Okay, so I'm not quite actually to the bitter end of the problem. I have to do my subtractions. I've got to do 0.5 minus x and 0.5 minus x, which obviously gives me the same number, 0.107. And my HI is 2 times x, which gives me 0.786. Okay, so the purpose of the ice charts is to allow you to figure out what pieces you need to put into your equilibrium expression before you do the algebra crunching. This is a multi-step process. So I have one more example that I want to go through today. This is an assumption issue. If you have information about QC and or KC, and they're both very small, we can make an assumption that allows us to simplify the math, but it only works. Okay, see the thing that I have in parentheses here? They must be less than 5% of your initial concentrations. If they're more, you're not allowed to use that assumption. So sometimes you can ballpark it and you get to the end and you go, oh, well, darn, it's 9.5% of my original. I'm going to have to go back and do it again and use the quadratic. So sometimes you don't know for sure to start with. All right, here's my equation. N2 and O2 gives you two NOs. I have a pretty itsy bitsy tiny Kc value. I've got 4.1 times 10 to the negative ninth. That also tells me that because the K is so small, I'm probably not going to get a lot of forward progress when I'm going to equilibrium. I'm probably going to end up with a little bit of products, but little being the operative word there, the value is probably going to be pretty small. I'm also not starting with identical amounts of reactants this time. I have 0.75 of my nitrogen and 0.5 of my oxygen. No products, no NOs. Kind of like the previous problem, I've got minus X and minus X because I've got to use a little bit of each one of those. But I need 2X for my product. At equilibrium, then I've got 0.75 minus X and 0.5 minus X and 2X. I can't even do my shortcut method of take a square root of everything because I don't have squareds on the bottom this time. All right, have a look at this where I have everything first set up this way. Okay, I've got my K value, 4.1 times 10 to the negative ninth. I've got my molecules there. I've got NO squared and then N2 and O2 on the bottom. I'm going to take all this information here from my equilibrium chart, and I'm going to put it here into my equilibrium expression. I got 2x squared on the top again, but I've got 0.75 minus x and 0.5 minus x on the bottom. Here is where I get to make my assumption. If you had a gallon of water and you took out 3 drops, you still basically have a gallon of water. Because my K value is very small compared to my concentrations. Go back over here and look at your concentrations. I've got concentrations of 0.75 and 0.5. That's fairly big compared to this value that's 10 to the negative ninth. So my assumption says on the bottom here, where I had the minus x's, I'm going to shortcut it. I am going to pretend that 0.75 minus x is pretty much just 0.75, okay? Like I said, back to the taking 3 drops out of a gallon idea. The same thing is true of the 0.5. Whatever number x is going to end up being is probably going to be awfully small. So I'm shortcutting it. Okay. This is what it simplifies down to here. I've still got the K value, 4.1 times 10 to the negative ninth. I got to keep some of my x's. I'm keeping the ones on the top, 4x squared. I'm getting rid of the ones on the bottom. I still have x's, but it makes the math less nasty. Multiply this together by bringing up the bottom 0.375 up to multiply times your 4.1 times 10 to the negative ninth. Divide by 4, take a square root. This is my x value. My X value is pretty darn small, especially in comparison. And I double checked it to make sure it did not exceed 5% of the smallest concentration there. The smallest of the two is 0.5. And so 1.96 times 10 to the negative fifth is 4/1000ths of a percent of 0.5. So yes, I am justified in my idea of, yeah, okay, I'm going to use the shortcut method on this. Sometimes you can, sometimes you can't. Like I said, there's occasions where you look at it and you go, I think I can shortcut it. And then you get down to this last step and you look at it. And for instance, if my X had been 0.1, 0.1 is 20% of 0.5. I would have to go back and use the quadratic formula and use all the messiness of that. So sometimes you need the quadratic formula straight up. Sometimes you have this situation where if everything is squared, which is what happened up here, you can square root the whole ballpark. And then sometimes you still set it up, but you can make it easier by using the assumption. So we've got 3 different scenarios or 3 different variations on how to solve for all the different parts of the equilibrium expression. Lots of nasty algebra. Yes, this is true. Okay. There's other things yet to come. We are going to talk on Tuesday about Le Chatelier's and some of the rest of this chapter. I know that this you're probably kind of staring at the screen going, blah. The deer in headlights look, because most people don't like equilibrium. In some ways, it's almost a little bit more evil than doing kinetics. The math is definitely a little more hectic. So just be aware that this is a very math heavy section, and unfortunately it doesn't really get a lot easier. We're almost to spring break. Okay, we have one more week until spring break happens. So we're at kind of the midpoint of the semester. Lots and lots of variations upon equilibrium occur for most of the rest of the semester. So this is kind of, here's the generalizations, then we're going to do acid bases, then we're going to do buffers and KSPs, and then we're eventually going to get into thermochem and equilibrium. And then hopefully, fingers crossed, the very last chapter of this, very last couple of chapters of the semester are electrochem and nuclear. I like nuclear chem. I think it's fun. Since I have everybody logged in now, any last minute questions about the kinetics homework, which is supposed to be submitted tonight? Take this weekend, start looking at your equilibrium homework. Like I said, we're not going to finish it until Tuesday, probably. And then homework for equilibrium will probably be due next Thursday. Some of you I saw last night for the Bolar mass of a solid, the Stinky Lab. And some of you I will see next week as the final lab before spring break. I have this weird, leery feeling because exactly this time last year, we all went, if you were part of TCC's community last year, we all went off to spring break last year, and then the world ended. It was like we never came back. It was just so bizarre. So I'm really hoping things at least continue at the pace they are post spring break. Any questions about lab? I know some people owe me things. So if you have not submitted the first 2 or 3 labs, definitely move forward and try to get them submitted as soon as possible. You can actually give them to me in person, okay? If you don't want to give them to me as the digital version, since I see you every 2 weeks, if you want to give me labs just as in like physical sheets of paper, that's fine. And that way I can rate them and then just give them back to you. And I just post them to Canvas as a number value without a submission. So if you have issues with trying to do, oh, well, I have a graph and I have a Word document, or I have a scan thing and a PDF, and you think you can't get it to work, paper is still okay too. I mean, I since I'm actually seeing everybody, fingers crossed, every 2 weeks for the remainder of the semester, don't get too far behind. Almost all of the labs this semester are very math heavy and very graph heavy. If you get too far behind, it's going to be a really mighty feat to catch up. Otherwise, I will see you on Tuesday.